Welcome to The Explainer. Today, we're going to break down this incredible paper that builds a powerful bridge between the deep, hidden structure of human language and the future of artificial intelligence. So let's just dive right in with a huge mystery. How on earth does a child, with barely any data, master the incredibly complex rules of grammar, while our most advanced AIs still trip up? Well, this paper has a radical new answer. All right, so to really get what's new here, we've got to go back to the beginning, to the theory that started it all, from the legendary linguist Noam Chomsky. So Chomsky's big idea, the one that changed everything, was this thing called universal grammar. He basically said, hey, we're not born with a blank slate. It's more like our brains come with a pre-installed operating system for language. This OS has universal principles that are the same for every language, and then parameters, which are like little switches that get flipped as we learn our own native language. Now, here's where it gets really interesting. Universal grammar makes this key distinction. It's a theory about competence, our perfect internal knowledge of the rules. It's not about performance, which is how we actually talk, with all the ums and ahs and mistakes. Think about it like this. Competence is knowing the rules of chess cold, absolutely perfectly. Performance, that's you at 2 a.m. making a dumb move because you're tired. See the difference? Okay, so that's the classic view. But now let's get to the new stuff. This paper gives us this really powerful way to think about it, asking us to picture grammar as a machine with 2 totally different layers. So first up, you've got the red layer. This is like the messy, greasy engine room, all the complicated step-by-step stuff that happens under the hood. It's the how. But then you have the blue layer. This is the clean, polished final product. It's the meaning that actually gets communicated and understood. It's the what. All right, so this whole red and blue layer idea, it leads us straight to the absolute core idea of the paper, a principle that's all about radical simplicity. And it all boils down to this one crucial point. What if universal grammar isn't some big, long list of rules we're born with? What if it's just a simple principle of, well, efficiency? The idea is that nature is kind of lazy in a smart way. It will always pick the absolute simplest or weakest internal red machine that gets the job done and produces the right blue meaning. And this simple idea just redefines the whole game. So those universal principles, they aren't some magic rules we're born with. Nope. They're just the bare bones connections you need after you strip away all the fluff. And parameters, the differences between languages, they're just symmetries, which is a fancy way of saying they're different, but equally good ways to say the same thing. Think the boy's dog versus the dog of the boy. The whole system is just on a constant hunt for maximum simplicity. That's it. Okay, so this is a super cool theory for linguists, right? But why should you care? Well, here's the twist. This is where it builds a direct, mathematical bridge to the AI that's literally changing our world as we speak. The paper uncovers something that is, frankly, astonishing. It turns out the math used to describe this weakest grammar idea is pretty much the same math that's running modern AI. The language of human sentences and the algebra of machine learning, they're deeply, deeply connected. Okay, so how does that work? Well, the first step is this. You can actually represent the meaning of a logical statement using math. Specifically, something called a tensor. Don't get bogged down by the word, just think of it as a fancy multi-dimensional spreadsheet of numbers. And here it is, the big payoff. You know those vector embeddings that large language models use to understand words? Well, an AI embedding is just a compressed tensor. That's it. It's the same fundamental thing, just squished down to be more efficient for a computer to handle. So this isn't just some cool thought experiment. No way. This connection actually gives us a concrete plan for how to build the next generation of AI systems. Right now, most AIs treat language like a flat string of words, like beads on a necklace. But we all know that's not how language really works, right? So this paper suggests something called a trace-structured memory. The AI would store language not as a list, but as a kind of dependency graph, more like a flowchart that actually understands how words are grammatically related. It's just a way smarter, more efficient way to structure memory. And the implications of this, they're huge. We're talking about a blueprint for AIs with way smarter attention, a memory that's way more efficient and structured, and an ability to learn better because it understands the deep symmetries in language. This could really lead to a more powerful, less clunky, and way more robust kind of AI. So, we'll leave you with this question to chew on. For decades, we've been searching for the secrets of language locked inside our own brains. But what if that ancient, super elegant code, that simplest possible system for making meaning, is also the very blueprint we need to unlock the next chapter for machine intelligence?